Now I'll discuss the solutions to the first assignment of analog circuits. The first problem, there is some current source, diode and some voltage source connected and so on. You are asked to think of the current source setting the operating point and this source as the incremental signal source. In all these problems involving nonlinear elements, there are two steps. One is to find the operating point, then to replace the nonlinear element by the correct incremental equivalent circuit and doing the incremental analysis. In this case, for operating point analysis, we short circuit this. So we have this circuit I naught, which is 2.7 milliamps, and a 2 kilo ohm to ground, and this side another 2 kilo ohms, that is 1 kilo ohm and 1 kilo ohm to ground, and here we have the diode. Our operating point model for the diode is to assume that it has a voltage of 0.7 volts. So that means that there is 0.35 milliamps through this resistor because it's 2 kilo ohms, and here also there are 0.35 milliamps flowing. So the actual current flowing in the diode is 2.7 milliamps minus these currents, which works out to 2 milliamps. So the operating point of the diode is 2 milliamps. Okay. Then at 2 milliamps, the diode can be represented by a resistor. Okay, this will go away and we'll have a resistor. And what's the value of the resistor? It is Vt by the diode current, which is 12.5 ohms. So this is 12.5 ohms. Okay, and this I naught is not there. So now we have a linear circuit. The peak value here is 100 millivolts, and you are asked to calculate the peak value of the output. So basically, you have to calculate the output when the input is 100 millivolts. That's all that's there to it. 12.5 ohms, 1 kilo ohm, and 1 kilo ohm. And this is linear network analysis. I'm not going to go through the steps of this. I assume you can solve for this quite easily in various different ways. And if you do solve for it, you will find that this voltage will be 0.308 millivolts, or if you round it to a single decimal place, it will be 0.3 millivolts or 0.3, which is the numerical part of the answer. Okay. Second problem, the circuit is exactly the same except that I naught is minus 2.7 milliamps. So what do we have? Again, assuming that the incremental source is 0, we calculate the operating point. We have a 2.7 milliamp source in that direction, 1 kilo ohm and 1 kilo ohm, and the diode is here. Okay. Now if you do assume that the diode is on, then there has to be a current flowing this way and that way, because this voltage will be 0.7 volts, and this way also because that is 0.7 volts. But then Kirchhoff's current law cannot be satisfied here. So the consistent condition is that the diode is off. Now actually that's enough to go ahead with the problem, but we can complete it nonetheless and see. If that's the case, then you will see that 1.35 milliamps flows that way and 1.35 milliamp flows that way, and the voltage here is minus 2.7 volts. Clearly the diode is operating in reverse bias. So the diode is an open circuit in the incremental picture because in reverse bias the diode incremental resistance is infinite, and the current source itself is also an open circuit in the incremental picture. So all we have is this 100 millivolts going through this resistive voltage divider, and you can easily see that what comes out here is 100 millivolts divided by 4, or 25 millivolts. That's the peak value of the sinusoid that appears here. So the output is 25. Okay, that is the numerical value of the voltage in millivolts. Our third question, it has 2 loops and 3 diodes, so slightly more involved, but nonetheless can be solved. If you are familiar with mesh analysis, you can kind of use mesh analysis here. Now let me call this current I1, this current is I2, and clearly this current will be I1 minus I2. This is the same as trying to do mesh analysis with this mesh current being I1 and that mesh current being. Now, there are 3 diodes. Consequently, there are 8 possibilities, okay, of any of the diodes being on, off, and so on. But let me first start with all diodes being on. If all diodes are on, then they can be replaced with 0.7 volt voltage drops. Okay. So here we have 19.4 volts, and here I have a 0.7 volt drop. Note the direction. It is from plus to minus of the diode. This is assuming it is on. So assuming all 3 diodes are on, each of them presents a 0.7 volt voltage drop. Okay. And V2 is 6 volts. Okay. Now, you can write out the mesh equations, or you can simply think of this current as I1 and this as I2. Okay. And if you write the equations around these 2 loops, you will get these 2 equations, which are 4 kilo ohms times I1 minus 2 kilo ohms times I2 will be 18 volts, and minus 2 kilo ohms times I1 plus 4 kilo ohms times I2 is 6 volts. I didn't explain how to write this, but I'm assuming you are familiar with linear circuit analysis. And if you do solve for this, you will find I1 to be 5 milliamps and I2 to be 1 milliamp. Okay. So this diode, the current going through it is I1, which is positive 5 milliamps. So it's on. The assumption is consistent for this diode. We assume that all 3 diodes are on. I2, the current flowing through this diode, it is 1 milliamp, also positive. So it's correct to assume that this is on. And I1 minus I2 is 5 minus 1, 4 milliamps. So this diode is also on. So our assumption that all 3 diodes are on is actually correct. And so these are the solutions. All 3 diodes will be on, and I1 and I2 will be these values. And you're asked for the power dissipation in Rx. The current flowing in Rx is I1 minus I2, or 4 milliamps. So the power dissipated in Rx is 4 milliamps square times 2 kilo ohms, which is 32 milliwatts. Okay. So the numerical part of the answer is 32. Now we have exactly the same circuit, but the values of V1 and V2 are different. And let's now see what happens if we again assume that all 3 diodes are on. Okay. So each of these will be replaced by 0.7 volts voltage drops in that direction. Okay. And the equations will turn out to be, again assuming that this current is I1 and this current is I2. So this current has to be I1 minus I2. If you write the equation around these 2 loops, 2 meshes, you will get 4 kilo ohm times I1 minus 2 kilo ohms times I2 to be 12 volts, minus 2 kilo ohms times I1 plus 4 kilo ohms times I2 to be 18 volts. And in this case, if you solve for it, you will find I1 to be 1 milliamps and I2 to be minus 4 milliamps. Okay. So this right away tells you that there is something wrong. I2 is in this direction going through the diode. It's the forward bias current through this diode, and that is minus 4 milliamps. So that really is saying that 4 milliamps is flowing in reverse bias through this diode. So what it means is that our assumption that this diode is on is incorrect. Okay. So we have to try other possibilities. So let's try this one. So because the diode current in this came out to be negative, let's assume that this diode alone is off. We don't know that yet, but let's assume that this diode is off. So in that case, if this diode is off, that means this current is 0, okay, because it's off. And we have just a single loop in which we have to do the calculation. Okay. So what will we get? We will get 4 kilo ohm times I1 to be 12 volts. Okay. So I1 will be 3 milliamps. Okay. So if it is 3 milliamps, we assume that this is off. So the current flowing here will be 3 milliamps. So that's correct. This is on. And the same current will flow into this. That's also 3 milliamps. So it's okay to assume that this is also on. We have to verify whether this diode is actually off. That we'll do. Okay, how to do that? If 3 milliamps is flowing here, across this you have 6 volts. And across this you have 0.7 volts. So between this point and ground, we have 6.7 volts. Okay. The current here is 0, so the voltage drop across this is 0. And the voltage between this point and ground is equal to V2, which is 18 volts. So you can clearly see that you have 18 volts on this side, 6.7 volts on that side. So this diode is indeed reverse biased. So our assumptions are consistent. This, by the way, you have to do after you calculate the solution, you have to make sure that your assumption for every diode is correct. So this is correct. And what is asked is the same as before, power in Rx, which is the current in Rx squared, that is 3 milliamps squared times 2 kilo ohms, which works out to be 18 milliwatts. Okay, so that's the answer. Okay, now in this case again another diode circuit with a different operating point arrangement. This you can think of as the source that sets the operating point, and the signal, the sinusoidal signal, is the increment. Okay. So now for the operating point, I have half a milliamp and a string of 3 diodes. Okay. And I also have half a milliamp here and 0.75 milliamps over there. So what do I get? In the first diode, the current is 0.5 milliamp. Okay. In the second diode, we have half a milliamp flowing from up here and also half a milliamp from here. So this is 1 milliamp, and this 1 milliamp minus 0.75 milliamp. This will give you 0.25 milliamps. So it's basically 3 diodes in a string, but different currents are flowing through each of them. In the incremental picture, of course, we won't have this half a milliamp source, but we'll have the signal source, which is 0.1 milliamp sine omega t. Okay. So all 3 diodes are forward biased. So that means that there is 0.7 volts across each of them. So the total voltage across the string of diodes is 2.1 volts. Okay. So that is this V0. So that's the answer to this question. The next question is exactly the same. You are asked for the incremental peak voltage. The incremental peak input is 0.1 milliamp. Here we have to calculate this. Now we have to draw the incremental equivalent circuit. We have already determined the operating point of each of these diodes. This is 0.5 milliamps, this is 1 milliamp, and this is 0.25 milliamps. In the incremental picture, we won't have this fixed source of half a milliamp, so we will have 0.1 milliamp sine omega t, and we have this diode, 0.5 milliamps is flowing through it. Okay. So it's represented by a resistance, which is Vt divided by the current, okay, which is 50 ohms. I assume Vt is 25 millivolts. And the second diode, this incremental resistance is 25 ohms. And the third diode, the incremental resistance is 100 ohms. Okay. Really simple circuit. All we want is this voltage. So it is 0.1 milliamps times the total resistance, which is 175 ohms, which gives you 17.5 millivolts. Okay, so the answer is 17.5. The next question, you are given a circuit with a source, a resistor, and a nonlinear element. The characteristics of the nonlinear element, the IV characteristics are shown here. The first part, you have to calculate the operating point, and from that calculate the power dissipated in this at the operating point. Okay. Now this kind of thing, it's very easy to do by graphical analysis. Okay. This is piecewise linear. You can also write the equations for straight lines in each of these 3 parts and then see where it intersects, where there is a consistent solution. But an easier thing is to, this is V, this is I, and do it graphically. Okay. So this is I. At the operating point we don't have this. So I will be 5 volts minus V, which is the voltage across the nonlinear element, or maybe V naught divided by 1 kilo ohm. And I plot that on the same axis here. You can clearly see that the y-axis intercept will be 5 milliamps, x-axis intercept will be 5 volts, and the straight line goes that way, and the point of intersection, you can calculate that. It will turn out to be where the voltage is 2.5 volts and the current is 2.5 milliamperes. Okay. So the voltage across the device will be 2.5 volts and the current through the device will be 2.5 milliamperes. So the power dissipated in the device would be the product of the two, which is 6.25 milliwatts. You are asked to give the power rounded to one decimal place, so it is 6.3. Okay. So that's the answer. Next question, exactly the same, except now you are asked to calculate only the sinusoidal component. Essentially you have to do the incremental analysis. In the incremental picture, this 5 volts goes away, that's a fixed part. We have the increment, which is 0.1 volt cos omega t, and we have 1 kilo ohm, and this has to be replaced by its slope at the operating point, and the operating point is here. Okay. The operating point is 2.5 volts and 2.5 milliamps. Okay. And what is the slope? You can clearly see that the slope is negative, and the slope is there is a fall of 1 milliamp over a voltage range of 3 volts. So the incremental conductance is minus 1 by 3 millisiemens, or the incremental resistance is minus 3 kilo ohms. Okay. So this is minus 3 kilo ohms. It's a negative resistance, and that's understandable. A part of this has negative slope, so you have negative resistance. Remember, this is only in the incremental sense. It says that if you increase the voltage, the current actually reduces. So in the incremental sense, you have a negative resistance. But if you have a total resistance that is negative, it will be generating power. But you can see that these characteristics, they are only in the first quadrant. So this element only dissipates power. But in the incremental sense, it's a negative resistance. It's very easy to calculate the output. The same as what you would do with the voltage divider, usual stuff, except one of the resistances is negative. So the voltage across this would be 0.1 volt times minus 3 kilo ohms divided by 1 kilo ohms minus 3 kilo ohms, which gives you 0.15 volts or 150 millivolts. So the numerical answer is 150. Okay, the amplitude in millivolts. The interesting thing about this is that the output amplitude, this is a resistive divider, but this resistance is negative. Because of that, this output amplitude is actually higher than the input amplitude. So in fact, this also behaves like an amplifier. That is, amplifier in the incremental sense. Okay. And in fact, it turns out there is a real device corresponding to this type of characteristic. Of course, it doesn't have the straight line segments. The characteristics will be somewhat smooth. It will look like that, and it's known as a, it will pass through the origin, of course. It is known as the tunnel diode. Okay. So when this negative incremental resistance in the tunnel diode was discovered, it was used for amplifiers and oscillators, and even now it is used. But it's not very convenient, because in an amplifier you would like to have two ports, that is, one where you feed the input, other where you take the output. Okay. In that sense, a two-terminal device which can be used as an amplifier, it's not very convenient, although it can be used. So it's not very popular. You have transistors which have two ports. You can feed the input from one side and you can take the output from the other side, whereas a two-terminal element like this, you have to feed the input to the same two terminals and also tap the output at the same two terminals. But it can nonetheless be used, and you can look up tunnel diode on the web for more details of this. Okay.